Hello, my name is Luis Alfonso Rodriguez Salinas, and I am a master student at the Instituto Politécnico Nacional in Mexico. And today I will present my work titled Development of a Gas Sensor for Acetone Detection in Breath for Diabetes Monitoring in Aeronautical Personnel. This research is part of my thesis project and focuses on development of a nanostructural sensor that can provide a non-invasive method for monitoring diabetes, specifically in the aeronautical environment. According to the Civil Aeronautical Medicine Manual, aeronautical personnel diagnosed with diabetes mellitus must maintain strictly glycemic control and undergo continuous monitoring. In this context, acetone has gained attention because it is a volatile biomarker found in exhaled breath directly correlate with blood glucose levels. Therefore, instead of an invasive blood test, detecting acetone in breath emerged as a promising alternative. Among the different sensing materials, tin dioxide stands out because it is a metal oxide semiconductor highly sensitive to acetone. This project proposed the synthesis and characterization of nanostructured tin dioxide powders to be later used in a gas sensor device. The main objectives of this work are the synthesize tin dioxide powders using the Sol-Gil method, and the second objectives are to perform structural characterization using X-ray diffraction and scanning electron microscopy. These steps are fundamental for obtaining a material with the required nanostructure and surface properties to be sensitive and selective to acetone molecules. Tin dioxide was synthesized via the Sol-Gil method using tin chloride pentahydrate as the precursor and double distillate water as the solvent. The precursor was dissolved under constant stirring at room temperature, and water was added step by step to control the reaction kinetics and reduce particle size. The solution was then dried at 100 Celsius degrees for 24 hours, followed by thermal treatment at 350 Celsius degrees for 2 hours in a muffled furnace. The chemical reaction and the stoichiometry of the synthesis are illustrated in Figure 1 of the poster. This diagram summarizes the transformation from the precursor to the final tin dioxide nanoparticles. The structural characterization via X-ray diffraction confirmed the successful formation of tin dioxide with a tetragonal rutyl phase. As shown in Figure 2, the diffraction pattern exhibit characteristic peaks at 26 degrees, 33 degrees, and 37 degrees, matching perfectly with the reference data. Importantly, no evidence of secondary phases was observed. We also notice a broadening at the base of the peaks, which indicates a nanoparticle size. Furthermore, scanning electron microscopy, present in Figure 3, reveal nodular nanoparticles with size ranging from 28 to 34 nanometers. This nanoscale structure is essential because it provides a high surface area, which is crucial for gas absorption and therefore for sensing acetone efficiency. In conclusion, the Sol-Gil method allows us to obtain nanostructured tin dioxide with tetragonal rutyl phase and nanometric particle size. These structural characteristics generate a high surface to volume ratio that enhances sensitivity and reactivity, making the material a promising candidate for acetone detection. This represents an important step toward the development of a non-invasive gas sensor for diabetes monitoring, particularly useful in aeronautical application where continuous health monitoring is essential. This research is still ongoing, and the next steps will include the fabrication of the sensor device and its electrical evaluation with acetone in control environment.